Hello everyone, my name is Asaf Nadler, and together with Jordan Garzan, we are presenting this talk titled Inline Detection of Copy-Paste Botnet CNC. Both Jordan and myself are data scientists and security researchers for Akamai Technologies. Our emails are listed below if you want to reach out to us after the conference. The agenda of the talk has three parts. In the first part, we'll define the term of copy-paste botnets, and then we'll discuss how to possibly shut down botnet communication to these botnets using inline URL filtering. In the second part, I'll display a system overview of a system that processes repetitive patterns of copy-paste botnet URLs to identify new botnets and shut down their communication. Lastly, I'll hand over the stage to Jordan to discuss the analysis of the system and the takeaways. Bots often communicate with their command control server over the HTTP or HTTPS protocol. Therefore, a common defensive approach to block botnet command and control communication over these protocols is by using URL blacklists, so that if a bot attempts to communicate with its command and control server by reaching out to its URL, and that URL is known in advance and listed within a URL blacklist, then we can block the communication. The primary drawback of URL blacklists is that they commonly suffer from a high false negative rate that is misses because they are not updated frequently enough, and therefore they don't generalize to new upcoming botnets. Therefore, we are interested in detecting botnet command and control communication over the HTTP and HTTPS protocol inline despite not using URL blacklists. This is where we define the term of copy-paste botnets. We know thus far that the source code of botnets and their CNC server is often leaked out and published online. There's a talk from BotConf 2018 called Mirai Beyond the Aftermath, in which the authors discussed at least 5 botnets whose source code leaked out to the internet. We also see in 2020 tweets and blogs about other botnets whose source code leaked out onto the internet. So from the perspective of bot owners, they would often choose to copy and reuse leaked source code to save development time and effort rather than develop a botnet from scratch. When bot herders copy source code of previous botnets, they also inherit some similarities to these botnets. So for instance, when we're looking at new variants of the spy command and control URLs, we're seeing a pattern that repeats itself. We're seeing that new URLs still end with a folder called main and a file called BT version checker. The question is, can we infer that if we see a new URL within HTTP communication that ends with main/BT version checker.php, can we assume that despite the URL not being listed within a URL blacklist, this is still likely to be a command-controlled URL used by a new variant of SpyEye? So with this question in mind, we're considering how can we detect and identify that this URL is indeed a new URL used by SpyEye. So one way of doing that is applying known system of malicious URL detection using classifiers based on batch learning, online learning, and representation learning. These approaches commonly rely on traditional machine learning and neural networks, which despite providing very good results, they are not very suitable to reside on high-performing HTTP proxies to scan inline communication due to their computational resources. So this is where we're kind of looking for a solution that is able to scan URLs and make a decision while still not resulting in a lot of latency and not blocking inline communication. The solution that we're aiming for is regular expressions because new upcoming technologies such as Intel Hyperscan allows taking a set of URLs, compiling them in advance to a model that knows how to run and is possible for running in real time on proxies. So the idea is that if we'll have a set of regular expressions, we can compile them in advance into a model using the Intel Hyperscan engine, and then we can put and deploy this model on an HTTP proxy and apply the regular expressions within the model to every URL that is browsed on the HTTP proxy. From this point on, if any URL matches these regular expressions, we'll be able to block that and therefore shut down the communication of the botnets. So therefore, our motivation is to design a system that does two things. The first of them is to identify URL patterns of command control CNCs, and the second one of them is to characterize these URL patterns using irregular expressions so that we can later compile the set of regular expressions that we produce into a model that can run on a high-performance HTTP proxy and block botnet communication. There are several challenges for reaching that goal. The first challenge is that we start by collecting data set of familiar and known command control URLs. So the data set that we compiled thus far contain more than 150,000 command control URLs that we want to learn from and generalize. So this poses a challenge of scalability for such a system. Moreover, these data sets are updated on an hourly basis whenever new CNC URLs are emerging. So we're in the process of scaling enough and identifying new command control URLs by collecting formerly known command control URLs at scale. The second challenge is that we're dealing with a trade-off of sensitivity versus specificity. That is, we want to produce regular expressions that are not too accurate to never generalize to new command control URLs, but on the other end, not too generalized to avoid blocking legitimate URLs and matching on them. And lastly, with regards to performance, which we already discussed, we want to create regex that will be able to compile in advance using an engine, for instance, like Intel Hyperscan, to provide acceptable performance and not something that is too complex that won't be able to run on a high-performing proxy without providing too much latency for the end users. Now we're moving to the overview of the system. The first point in which we start the system is constructing a language model of URL paths. So we start with a data set of URLs that we know to be related to botnet command control communications. And as stated before, we have more than 150,000 examples of this. The language model maps each and every one of these URL paths into a point within a large hyperspace. So within that space, points corresponding to URL paths are in proximity only if they share similarity. That is, they share sets of characters between each other. So for instance, if we're looking at the set of points corresponding to the malicious URL paths of SpyEye, all of them ending with bdversionchecker.php, we'd expect these points to be within proximity within the resulted language model. The second thing that we do is that we cluster points within the language model corresponding to URL paths. By this point, we have clusters of points corresponding to URL paths known to be related to command controls. Now we take every cluster and we transform this cluster into an irregular expression, which is just a set of OR conditions between all of the URL paths within that cluster. So for instance, for these examples with the BD version checker, we're starting with a regular expression that says it's either the first URL path or exactly the second or exactly the third and so on and so forth. Just a set of OR conditions for each one of the URLs. The output regular expression is naive because it's too specific, right? It's not able to generalize to anything else that's not showing within the cluster, but it describes very accurately everything within the cluster. At this point, what we're trying to optimize is compress that into a regular expression that is able to capture all of the URL paths within the cluster, but also able to generalize. We achieve that using a genetic algorithm proposed by Bertolli et al. Over 4 consecutive papers that attempts to shorten the regular expression that we created, that is the naive regular expression, and shorten that into a form that still captures all of the URLs within that cluster, therefore being able to generalize to new command control's URL paths. The main problem now is that the resulted regular expression might also match benign and legitimate URLs. Now, the genetic algorithm supports getting both URL paths that we want to match on and URL paths that we don't want to match on. But due to scale, we have a limited set of malicious URLs that we want to match on, but we have a very, very large number of URLs we don't want to match on. So the way in which we narrow that down is that we take the regex that we got before, the generalized regex, we apply it to real traffic, we see what it matches on it. If it ever matches on benign URLs, then we say specifically that we don't want to match for them and penalize the model for matching on these benign URLs. This penalization causes the regex to change so that it both match the command and control URLs within the cluster, but never matches the false positive in the benign URLs. And henceforth, we're solving this problem iteratively. So in each step, we either generalize the model or penalize the model for matching benign URLs until eventually we converge into a regular expression that matches all of the URL paths within each one of the clusters, but also never match benign and legitimate URLs that we have within our data sets. So at this point, I'll hand over the stage to Jordan to talk about the analysis of the system and the takeaways.
Thanks, Asaf, for presenting the first part. Hi, everyone. I'm Jordan. Here, we're going to dive more into the technical details. We're going to cover the distance between URL paths, the clustering, the regex generation, the setups, the results. So let's start with the distance that we use between URL paths. So the idea is to build this distance between path. What I mean by path is the last part of the URL, what is located after the domain. Basically, we need to fit this matrix, symmetric matrix. Of course, the diagonal is 0. And we use the Smith-Waterman. And I will explain why. Let's take a look at those 3 paths. And the question that I want to ask you is, do they look similar? I'll leave you 2 seconds. Of course, they have to be clustered together. So we need to find a distance that put them close to each other. Let's test Levenstein distance and Smith-Waterman distance. I didn't explain yet what is Levenstein and Smith-Waterman, but we can compute them. Between A and B, we have 1 for Levenstein and 28 for Smith-Waterman. Levenstein says basically how much the strings are different, whereas Smith-Waterman tells you how much the strings are similar. If we compute now the distance between A and C, for Levenstein distance we have 50, and for Smith-Waterman we have 20. So between A and B and A and C, for Levenstein we have a variation of 5,000%. So we cannot use Levenstein distance. Otherwise, those 3 will not be clustered together. So what is Smith-Waterman? It is used in the biology fields, basically to find, the basic use case is to find the common ancestors between 2 people. They compare the DNA sequences and they try to find nucleotides that share in common. So how do we get 20 between A and C? It's basically the longest best match, the red part, is 20. Of course, we have more parameters in the space Waterman. We have three parameters: match, unmatch, and gap penalty. Those are basically rewards that you give to the algorithms to make him find this alignment. If you have any question on it, we can answer after the talk. So we have three issues. The first issue is that Swiss Waterman can return any number between 0 and n, with n the length of the path in our dataset. Big strings can get bigger scores. This is basically the same issue. And the clustering algorithm works with edit distance, not with similarity distance. So first of all, for the first two issues, we need to normalize the distance by dividing all the distance by the max between the two paths. And this gives us a number between 0 and 100. And to convert the similarity distance to edit distance, we switch the distance with the absolute value. Basically, the 20 becomes 80, the 70 becomes 30, etc. Let's take a look now at the clustering. We have a distance, we can plot them, so we can cluster them. We can form groups. We use dbScan, which is a popular unsupervised clustering algorithm. It takes as a parameters two parameters, epsilon and minimal points. Epsilon tells you basically what is the minimal distance between two clusters to be between 2 points to be in the same clusters, and minimal point is the minimal number of points to create a cluster. And to dbScans, you can pass the argument Smith-Waterman, which is pretty cool. And so why dbScan? Here, as opposed to many cases in data science, we understand what is epsilon. We understand what is minimal point. If we choose epsilon equal 20, we are basically saying to the algorithm, okay, group the paths that are 80% similar. So in our case, we want to choose epsilon or minimal points. So it fits to our use case. In this part, we have the distance, we have the clusters, and now we need to extract the rejects. And for every clusters, we need to extract one rejects. And we play a game called Rejects Golf. Maybe those of you have played before. I will explain the rules. The goal is basically to catch a list of words with the rejects without catching another list of words. Here, on the screenshot that you see here, it's an API released by the researchers that wrote the algorithm we use that solve the game automatically with genetic algorithm. For example, on our left side, you have a list of conferences, and on the right side, you have a list of our names. And it found the reject C, capital R, capital E that fits. Of course, in our case, we need to catch, instead of conferences, we need to catch CNC path, and instead of not catching our names, we'll put the benign dataset. So what is genetic algorithm? I will go over it in 2 minutes. If you have more questions, you're more than welcome to ask after the talk. So the goal of genetic algorithm is to find the best solution to a function. In this case, it's called a fitness function. I will explain what is the fitness function. The difference between reinforcement learning basically doesn't use the classic gradient descent, and it's an iterative process that at each step apply evolution mechanism to find the best solution. Of course, you can find the best solution randomly, and it works, but this algorithm has proven results already. This is the flow. You start with a group of basic solutions. For example, one solution for rejects will be path 1 by path 2 by path 3, and then you apply evolution mechanism, which are crossover and mutation. Crossover is basically the mother and the father that mix their DNA to create children. And mutation, You take one solution and you just modify a part of it. And until you reach the criterion, we'll get to the criterion. So this is how they represent on the left side the regex. They represent it with a tree. This is a regex in Java. So for the Python guys that sees the plus plus, this is possessive quantifiers. It doesn't exist in Python in other languages, for example. And the two fitness functions are the sum of Levenshtein distance between detected strings and the desired string. We want to minimize this sum, of course, and the length of the regex. The shorter the regex, the better. I put here the parameters that they used and that we took and that worked well in our case. Instead, you want to reproduce. So we have the clusters, we extract the regex, and then we will test this regex against our benign dataset. If it doesn't catch anything, we keep this regex. Otherwise, we will retrain, we take the false positive, and then we put on the list to not catch. Remember the game, regex golf. We can do it n times, and after n times, if we still find false positive, we don't use this regex. It will be maybe clearer with the data. So we start with the data, the setup. We use the big machine on AWS because it's a CPU consuming for the Smith-Waterman computation and for the regex extraction. We used 106K CNC paths and more than 1 million paths of benign. We took it from Akamai, HTTP traffic, from Alexa, and public dataset. So again, the loop, we have the cluster on the left, we extract the regex, we create false positive, we took those false positive, we inject them into the algorithm, and we get another regex, same for another cluster, etc., etc., etc. This is how we get regex without any false positive. About the results, first of all, we did a cross-validation. We took all the data that we have until 2018, we trained on it, and we tested it against the data that we got after 2018. And we saw that from only 12 URLs, 12 paths, you can have 26.3% accuracy. Of course, without false positive. So it's very, very cool. You need only 12 paths to detect all the variants for these signatures. Even if you have more than 12, of course, you can see on the table, you get 100% catch. With this dataset, we ended up with 34 regex that detected more than 1.3K new CNC URLs. Also, we took those 34 regexes, we tested them against VT URLs, and we discovered 10.2 CNC there. Conclusion. So using a genetic algorithm and clustering based on Smith-Waterman and dbScan, we were able to construct 34 regexes that identify 1.3K new C2 URLs. For every clusters, you need only 12 URLs path to create a powerful signatures. Cluster regexes, the future work. We need to cluster regexes within the same family. So this is the next goal. And we are seeking of releasing the code that is a mix between Python and Java, because the part of the regex extraction is written in Java and our code is written in Python. I put here the link of the Java code instead you want to test it. Thank you very much. I hope you enjoy Q&A.